The title of this presentation is Dual Objective Functions, Exact and Approximate Optimality in Classical Quantum Gaps. So to begin with just a very brief recap of what was stated in the previous presentation in the series, we further built upon the semi-definite program formalism, including formulating or describing how to formulate dual STPs, namely by interchanging an infimum with a supremum or a supremum with an infimum, as well as interchanging the conditions that are used for the constraint optimization problem, in addition to the objective function. And pretty much the fact that in the case of the dual semi-definite program, it's a very convenient formulation to have from the original semi-definite program because the dual semi-definite program has some objective function that can be expressed in terms of the optimal value or the maximum probability of winning a game and up to other types of combinatorial factors, which we're going to further describe in this presentation or in this presentation of the series, the third presentation. And like we have been mentioning, this is relating to the fact that the structure of solutions to the semi-definite program for the 3 XOR game pretty much allows us to be able to construct more complicated primal feasible solutions and aspects, which I'm also going to further describe in terms of how many more constraints would someone actually have to pose or have to raise or use in terms of the criteria for the semi-definite program for, say, different types of multiplayer XOR games or even strong parallel repetition of the XOR game and FFL games, because we've also been discussing several aspects about strong parallel repetition across the first 2 previous presentations in the series. And as given in the second bullet point, associated with the 4 points in the previous item above, we discuss how the action of suitable operators, which can be thought of as intertwining or anti-commutation rules that appear in various error bounds and generalizations of error bounds. So it's pretty much in this bullet point, I was drawing the attention of the viewer to the fact that the error bounds, as well as describing how one would expect the optimal value to behave for some game, it's pretty much dependent upon the action of this suitable operator, which is just determining the order in which certain observables from players appear in tensor products, which are spanning some Hilbert space over the set of all possible over the tensor product of the set of all possible responses for each one of the players. And altogether, with such considerations in mind, we provide and discuss several characteristics of the generalized error bounds for a wide variety of games that were introduced in the first presentation of the series. So this is just a recap and kind of a general discussion of where the second presentation was going in terms of adding on some more characteristics into our intuition and actually formalism in terms of the semi-definite program and the notion of duality for the semi-definite program and how that actually relates in terms of the, basically the multiplayer XOR games and strong parallel repetition variants of the XOR and FFL games. And now I'm just going to very briefly recap some of the inequalities and some of the just mathematical expressions and relationships that were given in that second presentation in the series. Namely, again, drawing our attention to the fact that it was very important for us to obtain a desired collection of upper bounds for a system of Frobenius norms, where in this case, in the 2-player case, we have a tensor product of the identity operator with one of Alice's observables, which is acted upon by the suitable linear operator for the FFL game, and how that had a strict upper bound in terms of the Frobenius norm of this suitable FFL linear operator, in addition to the fact that there's some prefactor to this Frobenius norm of the suitable operator in terms of the square root of epsilon, namely the square root of epsilon approximality condition, in addition to some real multiple or some real number multiplied by n little n of squared, namely the little n raised to the number of players in the game. And then, but remember that this was given by the fact that given the constraints in what we're factoring into consideration from Alice's observable, which has to satisfy some certain conditions in terms of the upper bound being dependent upon the Frobenius norm of the suitable operator for the FFL game. The second type of inequality actually relates how Bob as the second player in the game can formulate some tensor and what one would actually have to perform some type of transformation to Bob's tensor observable B sub j of k for j not equal to k in the second term of the inequality from the lower bound of the Frobenius norm in comparison to the same type of operation that has to be applied to Alice's tensor observable. So this is just getting at the constraints that are in the most simple type of symmetric case for only two players, which is the easiest case to consider, and how this is actually relating to the actions of the suitable linear operator, and how, in fact, the specific form of the mapping that's given from the FFL operator for this game is given by a tensor product of two identical copies of the complex value space of C with dimension 2 to the floor of little n over 2, which is mapping into the tensor product of the Hilbert spaces corresponding to Alice's measurements and also to Bob's measurements, respectively. And the dual SDP, the dual semi-definite program with the objective Y, which again we're going to study and going to characterize further in this presentation, the third presentation of the series, is given by the fact that you're still going to perform some strong parallel repetition operation, but like I had mentioned, the fact that the original semi-definite program is defined in terms of a supremum. When you're passing to the dual semi-definite program by duality, you're going to end up taking instead the summation over as an objective function, the summation over the wedge, or the strong parallel repetition operation applied to each one of the question sets from each one of the parallel repetitions of the game that you're performing against the dual objective function little y sub q sub j of I, and then the constraints that are placed onto the optimization problem in the infimum which appear from these constraints are also related to the fact that they're taken as a summation of some condition that's taken with respect to the partial ordering of the positive semi-definite cones. So again, obviously, given the fact that before we were looking to form some dual semi-definite program, there was some partial ordering over the positive semi-definite cone, that same type of condition and same type of relation from the symmetrized gain tensor for strong parallel repetition, it's also coming into play here, which is undoubtedly demonstrating how, again, that original structure that we were talking about from the primal feasible solution Z prime for the 3XOR semi-definite program, it's coming into play, obviously, in the dual strong parallel repetition semi-definite program. And the FFL upper bounds on the Frobenius norm are related to the fact that, again, as I'm reminding the viewer from the previous result, namely that lemma FFL, strong parallel repetition, namely the fact that we can compute and obtain a suitable collection of upper bounds for the Frobenius norm of each one of the Frobenius norms in the system for the anti-commutation rule of the strong parallel repetition operation of the suitable linear operator, which holds up to some desired square root of epsilon strong parallel repetition FFL upper bound. And it's just basically given that, again, given the fact that, like how I had previously motivated in the first and second presentation, when you're looking at the FFL game in the two-player situation, it's very much a valuable type of game to look for establishing comparisons between strong parallel repetition of 2XOR games and how actually that relates to strong parallel repetition of multiplayer XOR games, and how one can leverage these different types of notions together simultaneously. And this is just given by the fact that obviously intuitively we can be able to form the strong parallel repetition of the suitable linear operator for the FFL game in terms of just a big wedge for only two strong parallel repetitions of the suitable linear operator. And then basically what we're doing is that we're establishing that same type of anti-commutation rule, namely, oh, sorry, there's a little typo here. There should be the the position of the identity operator within this tensor product should be switched with a twiddle, but it's a small typo, but it's still another typo nevertheless. But just the each one of the constraints that we place and the conditions that we place upon the strong parallel repetition version of the suitable linear operator, which is applied to the product of tensor observables that appear for each one of the two players, can be straightforwardly adapted from pretty much the two-player entity that I gave originally for the FFL game, which is relating to an extension of this type of observations from, behavior of approximately optimal and exactly optimal solutions or strategies for XOR star, XOR, and CHSH event games. And again, just to remind the viewer of another component, which I'll bring up to emphasize later on in the slide, when we've established some more generality to that dual semi-definite program formalism, is just basically given by the fact that we can also look to perform strong parallel repetition with holds up to some square root of epsilons, namely the square root of some sufficiently small parameter or some parameter that's taken to be sufficiently small, which is relating to FFL approximality, namely strong parallel repetition of FFL approximality, in the sense that we're having the first term, which is appearing in this norm that we would like to upper bound dependent on square root of big N, namely, or square root of N, namely the number of players in epsilon, and some prefactor, which is respectively given by some strong parallel repetition of the tensor observables comparing or that are consisting of Alice's responses, in addition to the fact that in the other term, when we're doing minus identity and looking at some type of interchange or intertwining relation like we've been mentioning and discussing for Bob's observables for the possible questions that he can offer for each player in the game, it's just basically given by taking the strong parallel repetition operation of each one of the tensor components or the observable components which appear from each possible set of responses that Bob can offer to the referee, like we had mentioned and described earlier. So pretty much the referee and the players themselves under parallel repetition or strong parallel repetition under both the ordinary and strong version of the operation, they're pretty much always playing a role in determining how whether the correctness of the player's responses can be applied or determined from just basically almost like independent trials or independent repetitions of the game that are taken in sequence, and how that can be related from an information theoretic and representation theoretic type of perspective. In the second example, strong parallel repetition, but for the XOR game, is given by the fact that, again, like we had drawn the attention of the viewer to in the last part of the presentation, we can look at a variant of this type of inequality by varying the number of strong parallel repetition operations that we're performing to each one of the tensor observables for any one of the players who's participating in the game, which in the presence of and given the optimal quantum strategy, which is appearing in both of these terms that we would like to upper bound with the norm, psi of 2XOR wedge, however many times the strong parallel repetition operation is performed with itself, we can also obtain some square root of n epsilon upper bound for some epsilon taken to be sufficiently small and strictly positive. In under strong parallel repetition, we are pretty much concluding the second presentation from the series by drawing the attention of the viewer to the fact that, as characterized for many game theoretic situations, the action of the suitable linear operator takes this form. Namely, we're trying to look to perform strong parallel repetition for the tensor observables gathered from one player and to basically interchange the order in which the suitable linear operator appears in this difference that we would like to upper bound under the absolute value, or the L1 norm, or with respect to the Frobenius norm. So basically determining the fact that the Frobenius norm is coming into play when we're looking for providing some upper bounds for each one of the strategies from the players participating in the game in terms of the Frobenius norm of the suitable linear operator itself is pretty much coming into play, namely that we're looking at this anti-commutation or intertwining relation taken with respect to a different type of norm and having some type of strict or a softer type of upper bound that can hold for these anti-commutation and intertwining relations with respect to different suitable operators. And ultimately, as mentioned in the first presentation, which is even kind of bringing everything full circle, so to speak, the structure of the error bounds and the generalized error bounds reflects upon invariance of the optimal value under parallel repetition, which again, like we've been saying, we've really been seeing this type of difference in terms of how the optimal value is likely to behave when we're going to perform strong parallel repetitions, namely whether the maximum probability of winning the game is going to be multiplicative, namely it's obtained as given in the first case from the XOR case by taking a product over the number of strong parallel repetitions little j of omega of XOR, namely the optimal value and the maximum probability under a quantum or classical strategy raised to the j, or also in comparison to the fact that the FFL game, the strong parallel repetition variant, remains invariant, namely the maximum probability of winning the game before performing strong parallel repetition or even performing after, or after performing it, they're actually equal, both equal to 2/3, which is signaling some type of invariance of the maximum probability and hence the probability of trying to harness some type of advantage of some quantum or classical strategy. And so now I'm going to provide an overview of the third presentation, namely, which is allowing us to further build upon characterizations of XOR, XOR star, and FFL games that are going to be developed, namely from the fact that we're going to introduce other aspects of dual semi-definite programs beyond their formulation. And this will allow us to discuss how exactly optimal behavior is determined by the structure of this type of dual objective function. And I'm pretty much going to provide pretty much provide as much more detail as I can in terms of the structure and the piecewise function definition that I've pretty much been describing extensively from the formulation and the statement of the dual semi-definite program itself from the second presentation, the previous presentation in the series. And this will allow us to basically contrast various multiplayer settings, which is altogether also allowing us to establish additional comparisons under ordinary and strong parallel repetition. And finally, we're going to conclude by establishing the advantage of a generalized error bound from four equivalent conditions of exact and approximate optimality into two-player settings. So again, we're kind of going back and forth between two-player settings and multiplayer settings and what type of information is helpful for us to dissect and to further quantify and to provide some upper bound for with respect to, like I mentioned, the L1 norm or the Frobenius norm, and how this relates to different types of game theoretic situations and circumstances that we can examine and study further. So again, this is just given by the fact that explicitly one formula for the dual objective Y is given by the fact that for the 3XOR game, like I defined and I alluded to previously, you can look at either the dual semi-definite program or the ordinary semi-definite program before passing to duality to obtain another type of equivalent function or another type of equivalent constraint optimization problem is that it's basically defined in terms of little n raised to the number of players like I mentioned. And this is just basically given by the fact that since we're taking a constraint over a summation of little I between 1 and NQ, like how it's been given here, we can obtain the solution to, or the exact expression to the dual objective function, which is appearing in the dual formulation of the semi-definite program in terms of just the optimal value omega-3 of XOR, which is appearing in all types of the entries of this piecewise definition for the dual objective function for or the objective function for the dual semi-definite program for determining the primal feasible 3XOR solution, but also given by the fact that, again, like how I mentioned and alluded to more in the first part of the presentation of the series, there's always this combinatorial type of normalization and coefficient, which is appearing in the denominator for the semi-definite program or various optimization problems that one is considering when we're looking at determining either the optimal value of some type of game from some constrained optimization procedure or actually determining the primal feasible solution or even the dual objective function when we're looking at either an ordinary regular SDP in addition to a dual SDP respectively. But besides the first line, which is defining the components of the dual objective function from 1 to little n, we can also have other types of two lines below this piecewise definition, which are describing the exact form of the dual objective function from the semi-definite program that we're passing to under duality, which is given by the components, the entries n plus 1 to n squared, which is just given by the fact that rather than the first n components of the objective to the dual semi-definite program that we're taking the infimum over, which is dependent upon little n in the normalization, we're having n times n minus 1. And then for the remaining components, we're having n minus n times n minus 1 times n minus 2, in addition to this combinatorial normalization from 3 factorial. So this is just demonstrating like how I've been describing even from partly from the first presentation in which we're going to want to make use of primal feasible solutions for the 3 XOR case. This is again bringing things a little bit more full circle and defining everything explicitly in terms of the main results that I listed in some table that I reproduced from the table in pretty much the first couple. There appears some type of combinatorial normalization that's proportional to in scaling with regards to the total number of players in the game that's appearing in these types of coefficients. But again, like we have been mentioning, rather than the fact that in the first n components there only includes a normalization of n, we can add on additional factors for n minus 1 and n minus 2 depending upon the n plus 1 component to the n squared component, as well as the n squared plus 1 component to the n cubed component. So again, this is just relating to the fact like how I've been emphasizing from different types of arguments, and that I will continue to for multiplayer XOR games with more numbers of players, that basically you're always recovering in the formulation and the explicit formulation of the dual objective function that you're trying to optimize over, just basically the optimal value of the game from the maximum probability of winning, in addition to the fact that you have some combinatorial factor from whatever number of players there is factorial, as well as some type of cascading multiplication, namely that's proportional to in scaling with the number of players, namely n or n times n minus 1, or as given in the n squared plus 1 to n cubed components of the dual objective function, n times n minus 1 times n minus 2. So this is exhibiting how different types of ways in different types of structures from the piecewise definition for the dual objective function for the 3 XOR game can come into play, and that will inform other types of comments and observations that we're going to be making later in the presentation. And as I had mentioned, still, a lot of times, even though we're looking at a 2 XOR game or a multiplayer XOR game, or even strong parallel repetition of an XOR game or FFL game, there can be a set of equivalent conditions, which is ultimately still relating to the collection of conditions that I originally looked at as an adaptation from Ostrov's framework for the XOR and CHSH of N games, which is ultimately relating to contextuality and non-locality, which is coming into the play for quantum information processing. So it's just pretty much stating that 4 types of equivalent conditions are going to be the same for the game. And I'm going to provide the first 2 conditions, which are given as equivalent characterizations for an epsilon approximate strategy, and basically juxtaposing comparison or making frames of comparison, like I'd mentioned, that type of approximality condition as the epsilon parameter in the threshold is taken to be arbitrarily small and eventually 0. And again, this is just pretty much relating to different types of ways that, even like how I've been alluding to and presenting on, and presenting as motivation to the viewer in the first presentation, in terms of looking at maybe from a statistical physics or other types of physics perspectives, in terms of pretty much a subcritical, supercritical, or exactly critical behavior, how pretty much that can relate to quantum classical gaps, like I've been emphasizing from the third keyword that's appearing in this presentation, and how this would actually end up relating to basically the optimal performance that different players can be able to achieve when they're participating in this game with either a quantum versus a classical strategy. So this is just given by the first condition, which is just saying that the first characterization of approximate optimality is given by the fact that we can look at an epsilon approximately CH of SH of game, which satisfies some condition, which is relating to one of these inequalities, which is shown in another second inequality, which I'll provide on the second slide. And it's just basically claiming, as given in the second bullet point, that a second equivalent characterization of the approximate optimality is given by the structure of these error bounds, which is just given by basically saying a summation over a square of the absolute value, or of a square of these two norms, where basically we're taking a difference of quantum states with respect to the L1 norm, which has an upper bound of 2n times n minus 1 epsilon. So again, this combinatorial aspect that I introduced, which comes into play for some part of the normalization for the dual objective function from the semi-definite program that we obtain after passing to duality from the original semi-definite program from the primal feasible solution. It comes into play here because basically we're looking at an epsilon approximate version, which is just basically saying that up to some constant dependent upon the number of players and some type of combinatorial contribution, like I mentioned, that's dependent upon this, that scales with regards to the total size of agents participating in the game with the referee up to some multiplicative factor up to epsilon. We have that this error bound holds, where basically we're looking at some type of superposition of Alice's states and interchanging the order in which they appear with Bob's observable for his set of all possible responses for the game, in addition to the fact that for the other type of contribution from the error bound that we're taking under the summation between I less than j less than or equal to n, but all greater than or equal to 1, for the summation index, we're looking at also a way to interchange the order in which certain observables from Alice appear in the superposition for the first term that's appearing with the tensor product with the identity operator, and subtracting off instead a tensor observable corresponding to Bob's responses to the referee, but instead J with the indices JI instead of IJ. So it's pretty much interchanging the order in which these two types of indices appear, which again is very much establishing an anti-commutation or an intertwining type of relation, and how that basically relates to several types of aspects and themes that we've been trying to emphasize with regard to the properties of suitable linear operators, and how that actually comes into play in terms of several types of error bounds that one would hope to be able to construct. But besides the first two equivalent conditions that I given in the previous slide, which are allowing us to characterize epsilon approximality for CHS H of n games, as well as epsilon approximality for the 2XOR game, given this epsilon threshold, there's also another type of inequality which can be obvious, or which can be pretty intuitive, that we should be able to conceive of, which is relating again to reversing the order of the tensor products for observables, namely the order in which certain of observables that players can gather for a game would actually appear in the summation, in the superposition of the squares of the L1 norms, which we're upper bounding with some type of constant, which is dependent upon the approximality threshold, some type of product dependent upon the total number of players of the game, as well as a combinatorial factor, 2 factorial, which is equal to 2 in this case, is capturing some type of possible number of ways that we can perform some type of way of mixing up or introducing some type of permutation to the order in which the observables from different players appear, which altogether is influencing the types of error bounds that we would like to be able to construct. And this is just relating to the fact, again, like I'm going to present on later in the last slide of the presentation, when we're looking at error bounds together at a glance, as I called the title of that slide, we can look at various types of comparisons to looking at how these types of combinatorial ways in which we can formulate error bounds, as well as the total number of contributions which are appearing from observables from different players which are participating in the game, which are ultimately seeking to maximize their individual utilities for winning when the referee is computing his or her scoring function V, how this is pretty much all relating to these three types of components that I've really been trying to strongly emphasize for the viewer from these types of three equivalent conditions. And lastly, the last equivalent condition, the fourth one, which is the same as the three previous equivalent conditions, is exact approximality, which, again, like we've been mentioning in establishing comparisons and alluding to in terms of the language of statistical physics is pretty much given by the fact that we're at some type of exact optimality or exactly critical behavior of some model or this game theoretic situation. And it's basically saying that these two summations, which I'd given in the previous inequality or the previous condition, the third condition on this slide, one of them is equal to the minus of the other. So one summation is equal to the minus summation of the other, where the left-hand side of the summation is given by, again, AI and AI plus AJ, whereas this same position that's given in the tensor product operators on the other side of the summation, it's given by AI minus AJ, as well as on the other side of the left-hand side, we have Bij and Bji. So again, it's almost like, again, another type of manifestation or another type of depiction of some type of anti-commutation or intertwining relation. But instead of with respect to some linear operator, some suitable linear operator, like we first demonstrated for forming an upper bound for the Frobenius norm for an FFL operator, it's actually relating to the fact that, again, it's actually literally applying to observables in the order in which they appear in tensor products, which are acting on the optimal solution state or the optimal strategy state for the players when they decide to use quantum strategies of quantum entanglement and other aspects of quantum information for being able to win the game. And again, for the second equality, again, we can expect that we're having some type of very similar relation, except that instead of forming a superposition out of the observables that Alice can gather, we're instead forming a superposition in the tensor product of operators from Bob's observables, namely Bij plus Bji divided by normalized by square root of 2. And then this is accompanied by AI in the previous term, whereas in the other term, namely the right-hand side of the second equality, we're having a minus of a summation over the same indices I and j, but instead it's AJ and Bij minus Bji normalized by square root of number of square root of 2, namely square root of the number of the tensor observables from the second player Bob. And pretty much this manifests in a lot of different types of ways for multiplayer settings, because you can imagine in multiplayer settings that there are, obviously speaking, there's a combinatorially larger and richer space of the total number of interactions that basically any groups of players can use to basically interchange their tensor observables, which are constituting the combinatorial nature and combinatorial contributions and how many factors are appearing under the summation that we would like to be able to upper bound for obtaining some type of error bound, which again is informing of and relating to the semi-definite program, the dual semi-definite program, the dual objective functions like I had provided for the viewer for the 3XOR game, and how this is altogether characterizing the main results that I had been emphasizing in the first presentation with that table, in which I pretty much drew the attention of the viewer to the fact that there are a lot of different types of ways to be able to characterize several types of theorems from this work, namely that they're all relating to primal feasible solutions of semi-definite programs and passing to duality and determining what is the nature of these dual objective functions and how ultimately it relates to the optimal value, the maximum probability of winning the game, making use of a quantum strategy. And again, I thought that was really helpful just to include this brief type of computation, because it's like a proof sketch of sorts, like how I had given in the previous presentation in this series, in the proof sketch in the previous part of the series, I drew the attention of the viewer to the fact that some type of computation that's proportional to a summation over contributions from each player that's multiplied by the optimal value is used to obtain some desired upper bound for the Frobenius norm, which I had established several parallels with in terms of the two upper bounds, like I had reiterated at the beginning of this presentation, in terms of the two upper bounds from the Frobenius norm from two inequalities resulting from the two-player FFL setting and the two-player setting for the FFL game, and how this is just basically relating to positive semi-definiteness along with the error bound, namely given by the fact that if we look at a symmetrized 3XOR game tensor, where again, I introduced in the previous presentation how to obtain a symmetrized game tensor from the ordinary game tensor, namely you take 1/2 of the representation with zeros along the diagonal and the transpose of the game matrix in the upper right corner, and then along the remaining element of the anti-diagonal, you take a G, namely the game tensor itself. And that with this symmetrized game tensor, with respect to the partial ordering of the positive semi-definite cone that we've been using and discussing extensively for being able to form well-posed optimization problems for primal feasible solutions of 3XOR games and beyond, even for arbitrary number of players, we can look at the summation with a contribution of terms from n cubed, sorry, that's a typo. It should be from 1 to 27, not from 1 to 9. But it's yi of e sub ii minus the symmetrized game tensor, and showing and demonstrating inherently that this type of operator is positive semi-definite is inherently at the heart of whether there exists some primal feasible solution and potential classical quantum gap, hence some potentially, hopefully, optimistically, some type of quantum advantage that players can make use of when they're playing the game. And pretty much this is given by the fact that when we're looking at this type of quantity, these E terms are inherently dependent upon and closely dependent upon a computation of the following form, in which we have some prefactor to some quantum superposition, where we're looking at the summation being taken over indices I sub 1, I sub 2, and I sub 3, respectively, over the question sets, or the set of all possible questions that can be distributed from the referee's probability distribution to each one of the players after the referee draws a question from his or her probability distribution with script Q sub 1, Q sub 2, and Q sub 3. And this prefactor is dependent upon the reciprocal, the optimal value, as well as some type of C coefficient, C of 3 XOR, which is accounting for, again, the combinatorial way of being able to introduce ways of interchanging player observables together for the 3 XOR game times a factor from n, little n, as well as a product from j being from 1 between 2 of n minus j. And pretty much this is allowing us to basically compute this following superposition, and to demonstrate that the following operator that I've given above for the 3 XOR game with respect to the partial ordering of the positive semi-definite cone is positive semi-definite. So pretty much it's demonstrating how like I've been describing, the positive semi-definite cone is a larger auxiliary space over which we're performing this constraint optimization procedure, how knowing the existence of the primal feasible solution, for instance, for this case of the 3 XOR game, it's really inherently related upon the computation and the properties of this superposition, where each one of these terms is pretty much given by a collection of states, which is very similar to what we had given and described in the first presentation of this series for the Bell states, or the EPR pairs. It pretty much as a hallmark or most simplified quantum system, which is demonstrating entanglement through the Bell states, or forming some type of generalization of the Bell states, because the first term that I give here, that I define here, u prime of I sub 1, I sub 2, I sub 3, it's given by a normalization of 1 over square root of 3 times a summation over ket states corresponding to the responses from each player to the referee's questions, while the v prime of I sub 1, I sub 2, and I sub 3 term is just a ket term of I sub 1, I sub 2, and I sub 3. And basically, if you compare the second equality and the second definition in the line that I've given from the first slide, or from the first line, you pretty much see that when you interchange I sub 2 and I sub 1 in the subscript of the u prime term, as well as in the subscript of the v prime term, it has, in the first case for the u prime term, it has the effect of obviously maintaining the normalization of 1 over square root of 3, while also switching the sign of the player 2 state in this ket superposition of player 1 state, player 2 state, and player 3 state, in addition to the fact that from the v prime term, it permutes the order in which I2 appears. So it's namely I2, I1, I sub I3, instead of in the v prime term that's given directly above the v prime term in the second line, in which this corresponding quantity in the first line, it's given by I sub 1, I sub 2, and I sub 3. And finally, you can even see that for the other remaining term, which we're using to define this superposition over the set of all possible questions that can be distributed to each player, is that we instead switch the sign on the last player 3 state. So this is just pretty much explicitly demonstrating how the dual semi-definite program and its formulation of some type of objective function, which under duality is taking the role of the primal feasible solution for the 3 XOR game, it's coming into play from this type of partial ordering with that's inherited from the positive semi-definite cone, and how it's pretty much also relating to some type of generalization and higher dimensional analog or counterpart of the Bell states and entanglement, and obviously equivalently as equivalent objects to the Bell states EPR pairs. And like we've been mentioning, exactly in the upcoming preprint, it's stated as the following, that the positive semi-definiteness from the partial ordering of the positive semi-definite cone is given by this result, just lemma T2 is just one of the many examples of a type of variant of this idea that I apply throughout the paper, in which I make use of Bell states and EPR pairs for being able to generalize or provide some higher dimensional analog or generalization or notions of entanglement and how that relates to exact and approximate optimality of different types of strategies. And is given just by basically saying that under the assumptions of the 3XOR error bound, the operator is positive semi-definite, namely the summation from one being between I and little n cubed, namely the dual objective function times this E term given by, which is object again motivated by that superposition over those possible states for U prime and V prime that I described extensively for the viewer in the previous slide, minus the symmetrized 3XOR game tensor. So this is pretty much demonstrating that this is exactly how the statement of the positive semi-definiteness result is given, and pretty much how this relates exactly to exact and approximate optimality, and how that relates to the 3XOR error bounds, which I generalized from the set of four equivalent conditions for the 2XOR game. And so again, this is just to say that obviously the explicit formulation of the dual objectives for the 3XOR game can straightforwardly be used to obtain other information about entanglement and related types of aspects of quantum information, which are used in the types of computations for positive semi-definiteness, and how that relates to the formulation of the dual semi-definite program. Because again, for the 4XOR game, the 5XOR game, and the NXOR game, which I provided for the viewer in the slide and reproduced from the preprint, we can see from 1 up to little n components, we have omega n of XOR of 1 over 4 factorial times 1 over 4 factorial times n. So again, it's just relating to the fact that we have a contribution from the optimal value of the game, as well as a normalization due to a combinatorial factor in the total number of players. And again, for however many number of components we have left for defining the piecewise function for the dual objective, we have n plus 1 to n squared, then we add in a normalization of n minus 1. And then even from n squared plus 1 to n cubed, we add in an additional normalization of n minus 2. And then finally, for n cubed plus 1 to n to the fourth, we also add in a normalization of n minus 3. So this is just demonstrating how the total number of terms which are appearing in the summation for a dual semi-definite program, and also the total number of terms that we're trying to argue from the operator like given for the 3XOR game as positive semi-definite, is really inherently connected to the form of the dual XOR solution, as well as the maximum probability for a player being able to win the game. And then obviously straightforwardly, the viewer can imagine that for a 5XOR game with, namely a XOR game with 5 players, or an XOR game, namely an XOR game with n players, we can have a very similar type of way, just depending upon some type of combinatorial normalization, namely 5 factorial, or even omega 5 of XOR, which is dependent upon the optimal value of a player winning a 5 XOR game with a quantum strategy, in addition to, even for the n XOR game, similar types of themes. And I apologize for the slight typo on this slide, but actually it shouldn't be the reciprocal of the optimal value, but it should be just the optimal value itself, because we can also look at, obviously, as another straightforward application of this framework that we've been describing, dual objectives under strong parallel repetition, which is given by the fact that for the n XOR game, we can just raise the number of strong parallel repetitions for the optimal value of the game, which is again proceeding and is also mediated by this combinatorial normalization big N factorial divided by little n, as well as being able to form all other piecewise entries of the dual objective for the n XOR game from the dual semi-definite program formulation, and how that relates to the operation of strong parallel repetition, as well as several types of analogs that we've been establishing. And then even for strong parallel repetition of the FFL game, like we have been mentioning and alluding the attention of the viewer to the fact that this optimal value of the game is invariant with regards to strong parallel repetition, namely that it's equal the optimal value of the game before and after performing the operation of strong parallel repetition is equal, actually implies just then that we have the first n components of the dual objective for strong parallel repetition of the FFL game being equal to 1 over 3 to the n, as well as the remaining components, namely from n plus 1 to n squared, being equal to 1 over 3n times n minus 1. So it's demonstrating how that type of very similar theme in terms of the dual formulation of the semi-definite program in the explicit formula from the piecewise function definition of the dual objective for the semi-definite program can be defined and written down explicitly. And again, like we have been mentioning, is that for the 4 XOR positive semi-definiteness condition is related to the 3 XOR positive semi-definiteness condition, in which, like how it alluded the attention of the viewer to, we have a larger number of terms which are coming into play in terms of the total number of constraints that we're trying to optimize over from the semi-definite program and the dual semi-definite program, which are coming into play in influencing how approximately optimal and exactly optimal behavior are arising. And it's given by the same type of condition, namely that we're also having the summation taking place from n cubed plus 1 to n to the fourth. So we're having that window of a larger number of terms which are coming into play for the positive semi-definiteness condition for the 4 XOR game in comparison to the positive semi-definiteness condition for the 3 XOR game. And like we've been mentioning and trying to tie up as we're closing the third presentation out, is that such inequalities resulting from the set of 4 equivalent conditions provide many characterizations of near and approximate or near and exact approximality, as initially discussed with the symbol error bound below. So this was one of the error bounds I given for 2 rounds of strong parallel repetition for the FFL game, because it has an upper bound of square root of n times epsilon up to some prefactor 20. And basically it's just showing that if we form some strong parallel repetition of a sub k and a sub k prime tensor product with identity minus the identity times the tensor product of these terms from some type of parallel repetition superposition of Bob's tensor observables from the set of possible responses that he can provide to the referee. This is ultimately relating to and complementing our notions of exact and approximate optimality and how that relates to the piecewise definitions and the piecewise functions for the dual semi-definite objectives, which we've been obtaining from semi-definite programs that we've been passing to under duality and motivating from different several types of perspectives. And again, this is just to close out the fact that optimal quantum or classical strategies can present several different possible characteristics and advantages for a player. And in particular, the case that now we can really see that we're making use of quantum optimal strategies in comparison to just some of the types of aspects that, of classical information. It's really coming into play in terms of just framing well-posed optimization programs that are taken with regards to the partial ordering of the positive semi-definite cone, and in particular how this is even relating to, again, these types of quantum states for the 3 XOR game, the 4 XOR game, the 5 XOR game, and the n XOR game, namely psi 3 XOR or kep psi 3 XOR, kep psi 4 XOR, kep psi 5 XOR, or even kep psi n XOR, which is ultimately relating to a union over all of the possible players or agents in the game and taking a supremum over their possible strategies. And as we're closing out the third presentation of the series, as some type of view from the first, second, and third presentations of the series together simultaneously, we can understand basically that these types of aspects of quantum information, namely entanglement or performing some intertwining or anti-commutation relation or operation, they're basically coming into play in terms of drawing our attention to what are the optimal values of these quantum strategies and how they can actually come into play for our studies and further examination of quantum information. And so the error bounds at a glance, like we've been saying, is that we have these error bounds for the 3 XOR game, the 4 XOR game, the 5 XOR game, and the n XOR game. And it's just basically given by some type of combinatorial contributions like we've been mentioning, 6, 4 factorial, 5 factorial, and big N factorial, as well as a product over the number of players, in addition to the epsilon approximality factor for the 3 XOR game, namely epsilon 3 XOR, epsilon 4 XOR, epsilon 5 XOR, and epsilon n XOR. And again, this is just characterizing how this is one of the equivalent characterization or characteristics and characterizations of nearly approximate and exactly approximate strategies that had eluded the attention of the viewer to in the 2 XOR setting, and how that's actually relating to some straightforward generalizations from positive semi-definiteness conditions and partial ordering with respect to the positive semi-definite cone for 3 XOR games, even up to big N of n XOR games. And so finally, as an overview, is that to further describe the property of dual objectives Y introduced from semi-definite programs under duality in the previous presentation, we continue juxtaposing assumptions that can be placed on different multiplayer games
and we discussed the piecewise definition first for the 3 XOR dual objective that we used to establish several types of characteristics and parallels between dual objectives for strong parallel repetition of FFL and XOR games alike, which allowed us to establish connections with exact and near optimal behaviors from the error bound discussed in the second presentation. And altogether, the formulation of the dual semi-definite program implies that different regimes of behavior, namely strategies that players can adopt, as well as the influence of these strategies, which are impacting not only sources of potential quantum advantage, but also classical quantum duality gaps. And thanks so much for your attention and listening to the third presentation of this series.